Yeah, first of all, thanks for that opportunity to give some insight in our current work. It's very interesting for us to also listen to those talks. And actually, I made plenty of notes today already. And I apologize for contacting you, or at least some of you, after that conference. So be aware of that. We are talking about some topics in regards of multimedia, information retrieval, and query construction and result presentation. So actually, I'm following the typical setup of those talks by just saying why we are doing things, what we did already, and what we plan for the future, or also in the context of this presentation, how we did it and what's coming up. So I think this is nothing very special, but we all have to be aware that currently in multimedia information retrieval, we are facing numbers that are so high, unseen in history, and all of us are related to these topics. And it's, for me personally, it's always astounding to imagine that 40 million WhatsApp messages are sent per minute. This is so incredible. And the impact on the solutions we have to build, on the algorithms, on the hardware, on the infrastructure, they are just overwhelming. And starting from that, we tried to find ways to increase the efficiency, to increase the effectiveness of multimedia algorithms. And we ended, well, not actually ended, but we came to a mathematical approach we call graph codes, which helps us to improve performance a lot. And based on this approach, we had to build a kind of infrastructure based on models, on algorithms, on matrix, on anything you need for information retrieval to utilize these graph codes also for your applications. And what I want to do in this short presentation is that, first of all, I will briefly explain the concept behind those graph codes and the adaptation to existing multimedia information retrieval applications. Because the challenge for querying and result presentation is always the same. We have a combination of different multimedia types for querying. We want to have fast and easy to use query interfaces, effective search results, including recommendations, and of course, the level of detail for search refinement has to be increased a lot due to the vast amount of newly created content. Yeah, and here you see a brief overview of what we call graph code. Basically, a graph code is based on what all of us know, multimedia feature graphs. And we discovered, as most probably also all of you, that searching and retrieval based on graph traversal algorithms is not the fastest thing you can do. In fact, the performance of these algorithms is very poor, especially if you want to achieve a high level of detail. You will not be happy with graph-based algorithms. And therefore, we invented a projection into a two-dimensional space, which actually is illustrated here on the right upper corner in this picture. And this projection helps us to perform mathematical operations in a much more efficient space. And we call it graph code because it's actually representing the features and the connections of a multimedia feature graph. So we have a vocabulary, which is illustrated here, and the vocabulary actually represents the features. And we have connections between those vocabulary terms, which is represented by the edges or the edge values in this kind of valuation matrix. So there is a function that is able to summarize this, to use a multimedia feature graph and to transform it into a very easy calculatable space based on valuation matrices. So, and the semantics behind that still remains. So every feature that has been detected, for example, in an image, is still represented in the graph code, but it's much easier to calculate on these mathematical concepts. And what we did in following up this concept is shown here. The advantage is that 2D space operations perform linear instead of exponential, which is great when we have to deal with a high level of detail or a lot of number or a high number of assets. And both is valid for multimedia information retrieval. In addition, graph codes support a high level of parallelism, as each of those cells within the matrices can be calculated or compared separately from each other. This also allows the utilization of current hardware like graphic cards, GPUs, or even AI chips, which are in iPads or smartphones or wherever. And for multimedia information retrieval, of course, we need measures for similarity. And to do that, we had to introduce a graph code metric, which helps us to compare assets represented by their graph code representation. And we discovered that to compare assets, it's not just enough to compare the vocabulary terms, meaning the features that have been detected. It's even more important to compare the relationships between those features. Because if you detect a person and a head, for example, we have to define the relationship. And if the head is above the person or next to the person, that might be very important for information retrieval. And therefore, we invented actually 3 different matrices. First one is based on the vocabulary terms, comparing what is in a picture, what is in a video, or what is in a text. The second one is based on possible relationships between these features. Because if you have a person and a head, it's always better to know that those have some kind of relationship, even if it's not exactly the same relationship. But even the information that there is some relationship is important for us. And the third type of metric is based on the relationship type, which actually compares if a relationship between 2 features is identical. And based on this set of metrics, we can calculate similarity or also recommendations, which will be shown later in that presentation. So basically, one step back, based on these metrics, we are able to perform multimedia information retrieval algorithms in a much faster way as compared to graph-based traversal algorithms. So having this, we have to deal, of course, with use cases, with what to do with an application. And in the context of this presentation, we were talking about those colored ones. How can we construct queries based on graph codes? Manually, query by example. How can we adapt queries? How can we deal with relevance feedback? And how can we present the result, which is actually calculated based on graph codes, meaning much faster and much more accurate? And to define those use cases, or actually to work on those use cases in the context of our presentation, we applied storyboards, which actually perform in a similar way that we all know from current and existing multimedia information retrieval applications. So there is no really new invention here, but the adaptation to the concept of graph codes, of course, has to utilize what we have with matrix, what we have with the mathematical concepts, what we have with parallelism, and so on. And Yeah, here you see two exemplary use cases, like the query by example use case. When we have a list of assets, we select an asset, and actually the query by example is performed on the graph code and not on the asset itself. And the graph code, by the way, is calculated by applying several multimedia detection plugins. So we are using Google Vision AI to detect objects in images. We are using, for example, several textual plugins that we implemented to apply text detection algorithms. We are using landmark detection. We are extracting EXIF and MPEG-7 metadata, all in all to find features. And our multimedia feature graph fuses and integrates these features in order to provide a much higher level of detail than current MMRR applications are able to produce. So when query by example based on graph codes is performed, you just get a higher level of detail and a much faster result. The presentation as a ranked list, yeah, that's something we know already. Similar with a manual query construction. In manual query construction, the user can enter keywords. Actually, when entering keywords, a graph code is created in the background, which just represents the keywords by its columns. And then this graph code is applied as a query by example, still performing a ranked list or still returning a ranked list of assets. But additionally, we are also able to support, for example, SparkQL, as the graph code concept can be extended in a semantic way to be compatible with RDF, RDFS, ontologies, and whatever you need in that area to do semantic search. And in this case, we can also utilize standard existing query languages. Of course, only few users will really go to the system and enter a SparkQL query. But SparkQL opens a whole new set of additional applications that can be used with or that can use graph codes. Yeah, here we have another option, especially when we deal with semantics or when we deal with a global vocabulary of terms. Then the user is able to display all the terms, draw edges between those terms to select even the next level of graph codes, not just the vocabulary, but also the relationships between those vocabulary terms. And then, based on the selection, another graph code is calculated to be performed as a query by example. So these are the storyboards. Here we have a very interesting thing if we talk about similarity and recommendations, because it's always a bit hard to distinguish between them and to calculate what is a recommendation and what is similar. And actually the metrics we defined for graph codes help us with that. Because in case of similarity, we try to find the best and most exact match of other images or assets or text or whatever you have. In case of recommendations, we can use the second metric we defined, which is based on the relationships and the relationship options between features that have been detected. And we discovered that when we apply that second kind of metric to our query, we will actually find a very good representation of recommendations based on the first asset. So this is a very interesting thing, and we have quite promising results here in our tests. And the advantage is that the implementation is very easy, as you see here with these two algorithms. Basically, it's actually just another order of that metric triple we have here. Yeah, we did a prototypical implementation. which actually covers almost all of the aspects that are presented so far. Here you see an example where you can query based on keywords in our application. And when querying city and water, you receive images that are somewhere containing cities and or water. So this is basically, yeah, let's keep it as it is. You won't win anything with that. That's typical. But here we see recommendations and similarity. And when I select the upper asset, for example, you see the difference. In the recommendations, you also might get an image with a horse, because for some reasons in this horse image, there is a relationship between detected features that is also in the above image. I would assume that in this case, it's the blue sky and the area where the horse is running on, because that might be even somewhere left to that river. So this detection shows that the recommendations also on a basis of images really work. Of course, if we would apply that to text, which we did, the recommendations are what you see typically on text-based retrieval systems. But as graph codes are multimedia features, or based on multimedia features to be more accurate, you can utilize them for recommended images, recommended videos, anything that is a multimedia object and has something to do with the object you placed in as a query by example. Our whole application contains much more currently. We also built a short graph code viewer to illustrate what has been detected from a selected or from a given image. Actually, this is nothing I would present to the user, but for our research, it's very helpful to see actually how these algorithms work in real life and what features are applied if we make a query by example or a keyword search or anything from a structured language. We are also currently working on natural language processing to SparkQL. But this is something that will come in future work. But the first results are also quite interesting. And based on these technologies, we are able to perform high level of detail queries on a large number of assets in a very short time. And this is, I think, one very important advantage that can be also utilized for many other applications or in many other research areas. So what is coming next? First of all, graph codes can act as a foundation for query construction and result presentation. We saw that, we built a prototype, it's working, and it could be implemented also for other MMIR applications. Second, the graph code metric is a very, very interesting thing, because with that metric, we can apply algorithms for similarity and recommendations in the same way and actually reuse lots of the applications that have already been built, because we just have to switch the algorithm. Of course, we make all of our work available at GitHub currently, and also in regards of other papers. And if you want to, you can stay tuned here. In our future work, we will evaluate more UI models and also try to implement this interactive building of graph codes, like selecting features or feature vocabulary terms and drag and dropping relationships between them, because we want to understand if this could be a query construction mechanism that is applicable to users and to UIs of other MMIR applications. A semantic extension and mappings to the semantic web are currently work in progress. And also here we see two aspects. The first aspect is that we can widen the application to utilize existing standards out there and to utilize existing tools. And the second aspect is that lots of information from an asset can be moved to the semantic model. So by integrating semantics, we can also provide a compression of these graph codes, which will additionally lead to even faster performance without losing any accuracy here. And the third topic we are currently working on is the integration of further multimedia types, for example, videos. We are here working on shot detection algorithms and try to extract keyframes, key objects, moving objects, and all those things that are relevant to query contents of a video. So I try to speed up a bit to keep your time, actually to keep the time I was spending with asking before. So I think we're quite good in track right now. Thank you for your interest and the opportunity to tell you what we're doing. Are there any questions here?